Okay, Assalamu alaikum, and let's start today for our lecture. This is the chapter number 11. We have been continuing from the last two lectures, and we are going to continue further today. Just as a small recap, last time we solved a problem. It was a big problem actually. It was a big numerical that we solved, and it was related to a counterflow concentric tube heat exchanger. So we had a counterflow concentric tube heat exchanger which was used to cool the lubricating oil from a large industrial gas turbine. Okay, the flow rate of the cooling water through the inner tube. So inside we had the inner tube, and within the inner tube we have the cooling water. While the flow rate of the oil through the outer annulus, and in the annulus region we had the oil, which was hot, which was being cooled. Okay, the flow rate of the overall flow rate of the cooling water and the lubricating oil was given, and the oil and water entrance temperature. So T hot inlet, T cold inlet was given, and it was required to know that what should be the tube length if the outlet temperature of the oil is 60 degrees centigrade. So the T hot out is also given. Okay, and we wanted to find out the length. We are not solving this problem again. We solved this problem. We spent a lot of time solving this problem in the last lecture. But the thing is that I just want you to recap what was asked in this problem, because the next problem is similar to this problem, except that instead of using counterflow concentric tube heat exchanger, now we need to use the plate heat exchanger. Okay, so now we don't need to use the concentric tube counterflow heat exchanger. Now we will be using the plate heat exchanger. Okay, and solve the same problem again. So did you recall back what was there, what was asked in the problem that we solved last time? Now let's go back. Okay, this is the problem that we are going to solve now. The counterflow, this is again counterflow concentric tube heat exchanger, the counterflow concentric tube heat exchanger of example 11.1 is replaced with a compact plate type heat exchanger. So now we replace it with the compact plate type heat exchanger. If you remember plate type heat exchanger, we have multiple layers of plate one over the other, and between two layers we make the hot fluid to pass through. Then between the next two layers we make the cold fluid to pass through, then hot fluid, then cold fluid. So it's like that, alternating. Okay, so is replaced with a compact plate type heat exchanger that consists of a stack of thin metal sheets. What kind of metal sheets? Thin. Thin means thickness is not given. Metal sheet thickness it's so thin that it's irrelevant. It's not going to provide any conductive resistance. Okay, separated by n gaps of width A. So obviously we have metal plates. So it's like this. We have stack of plates, so many plates, and the gaps between these plates is A. This is the gap through which you make the fluid to flow. So on one side you make, let's say, the hot fluid here, cold fluid, hot fluid, 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 like this. Okay, so the oil and water flows are subdivided into n by 2 individual flow streams. Obviously, if we have n gaps, so n by 2 gaps will be with the hot fluid, n by 2 gaps will be with the cold fluids.
So 2 gaps for one fluid?
2 gaps, no. If we have 100 gaps, so 50 gaps will have hot fluid in them, and 50 gaps will have cold fluid in them. Okay, it's like this. with the oil and water moving in the opposite direction. So it's again counterflow. Okay, so oil, let's say, is moving inside, so water is moving outside. Okay. It is desirable for the stack to be cubical geometry. So we want the stack to be cubical geometry. So it's like this. So we want it to be cubical. Cubical means, what is a cube?
The length and the width and the
Height, all same dimensions, okay?
Yeah.
So it's just one dimension. All three will have the same dimensions, okay? So it's L here, L here, L here. We want it to be cubical, okay? With a characteristic exterior length L. So now we have only one dimension here, L, which is the same as the width, which is the same as the length, which is the same as the height. Determine the exterior dimension of the heat exchanger. Now we need to find this L, dimension of the heat exchanger, as a function of number of gaps. So we need to find L as a function of N. We need to find L as a function of N. Inlet temperatures and the desired outlet temperatures are the same as in example 11.1. That's why I reviewed back example 11.1. The inlet temperature of the hot fluid is the same as in the previous problem. The outlet temperature desired is 60 degree. Inlet temperature of the lubricating oil was 100, outlet was desired 60. For the cooling fluid, inlet temperature was 30 degree. Outlet temperature was unknown.
Not 50, 55, I would think.
30. 35 we took the average to find the properties. Okay, and those steps we are going to do exactly the same way for finding the outlet temperature, and then after that finding what is the Q. So those steps would be the same as in case of the concentric tube counterflow heat exchanger, as in the last example. Okay, now compare the pressure drops of water and oil streams within the plate type heat exchanger to the pressure drops of the flow streams in the example 11.1 if 60 gaps are specified. Okay,
Now we give an N.
that's the second part. If N is 60, then compare the pressure drops. Okay, so first thing first, we need to find L as a function of N. Okay, N are the number of gaps, total number of gaps. L is the characteristic length. So this is L, this is also L, and in the third dimension it's also L. Do you understand the problem statement or not?
Yes.
So now instead of using concentric tube counterflow heat exchanger, we want to use the plate type heat exchanger. There we also wanted to find L, length of the concentric tube. And now here we also want to find the length. Okay. Now the thing is that between any two plates, what kind of flow we have? It's an internal flow. But it's now the cross section is not, now the cross section is not circular. Now the cross section is rectangular. Okay? Well, if the cross section is rectangular, so in chapter number 8 we had a table if the cross sections are different types. Okay? And for rectangular we had many options. And the options were all based upon B upon A. B be the length, A be the thickness or the width, you can say. Okay, so here in this case we don't know the overall L, so we also don't know what is what is the gap here. A.
Should be 1. Should it be 1?
No.
Take ratio.
Now the thing is that we know one thing, that there are many gaps within this length.
Total.
Hmm?
The total is L.
N multiply A equal.
So we have many gaps within this length. So we can assume that A is very, very small compared to L. A is very small compared to L.
Yes.
Okay. So if we have this case that A is very small compared to L, So it's like a case of flow between two parallel plates. Flow between two parallel plates, but length not defined. Okay? So that kind of case is there in the tables, table 8.1. And for that case, if now again we have to assume that we don't know whether it's laminar or turbulent flow, but that table is only for the laminar flow, and we are assuming that it is laminar flow right now. And most of the time, when you have small gaps, multiple small gaps, and the flow is divided between them, the flow becomes laminar between such gaps because it's divided. Okay. So for that case, the Nusselt number is 7.54 directly from the table. So go into the table. So for example, let's go into the table to show you. That was the table. And in this case, it was all, we have B by A ratio. And for B by A ratio, which is infinite, this one.
Can you make it to scale?
That's a B by A ratio infinite. For that case, for uniform surface temperatures, the Nusselt number value is 7.54.
How do we know it's uniform surface?
It could be assumed as uniform surface temperatures, because for the cases of uniform heat flux, you have a certain source of heat flux all the time. Whether it is solar, whether it is electrical heater, you have a certain source of heat flux all the time. But we don't have any certain source of heat flux, and we know a specific temperature which is being flowing through the tubes, so we assume that it's a constant surface temperature. Is clear? So it is 7.54. Let's come back here. So Nusselt number is 7.54, but Nusselt number is equals to h d upon k, right? What is hydraulic diameter?
4A over P.
Exactly. Hydraulic diameter is 4a upon p. Now, what is cross-section area here?
80.
Hmm?
80.
Yeah, a into L, you can say, because this length is L and this is A. Okay, so cross-section area is A into L. What's the parameter?
2L, 2A.
So 2 into A plus L. You remember I discussed one thing before with you guys, that if we have one very big number, one very small number, then there is an effect when we multiply, and there is another effect when we add them together. If we add them together, we can neglect the smallest number. If the two numbers are, one is very big, one is very small, then for adding them we can neglect the small number. But in case of multiplication, we cannot. So since here we already made this assumption that A is very, very small compared to L, so here we can neglect this A. Right? So if we neglect this A, it becomes what? 2L. L will cancel. 2 will cancel with this, so it becomes 2A. It's clear? So a hydraulic diameter becomes 2A. Hydraulic diameter becomes 2A. Is it clear? Now I can substitute the values, but A is what? We have to put everything in terms of L and N. Okay? So if this total length is L and there are N number of gaps, then A is equals to L upon N. Right? If this total length is L and there are N number of gaps, then A is equals to L upon N. Okay? So hydraulic diameter becomes what? 2A, which is equals to 2A will be L upon N. Right? So now this is my hydraulic diameter. It's clear? A is L upon N. I just want to put everything in terms of L and N. because I need to find L as a function of n. Is it clear? Now I just substitute the values here. Okay, I just substitute the values here. So what's written here? 5.4. Yeah, it's not kilonewton. Okay, it's Kn. K is this K, N is when you substitute the value 2. Okay, that's not kilonewton. So we get this thing, 2.36 into N by L. This is for the case of water. Similarly, for the case of oil, because on in half of the sections we have water, in other half we have the oil. For the case of the oil, we'll get this value. Okay. So that's HC and HH. Okay. Now we need to find out the overall heat transfer coefficient. What's the overall heat transfer coefficient? Okay. On one side we have the hot, other side we have the cold. Okay. So heat will be flowing from hot to the cold. Similarly, heat will be flowing from hot to the cold, right? So as the heat is flowing from hot to cold, okay, so what do you think? The plate thickness is negligible, okay? The plate thickness, so only we have the hot side convective coefficient and we have the cold side convection coefficient. And the areas are also the same because this is a plate, okay? So we have overall convection coefficient will be 1 upon 1 by Hc plus 1 by Hh. Is it clear?
Yes.
That will be the convection coefficient. Now we have this formula, Q is equals to UA delta T Lm, log mean temperature difference. That's the main formula over which we are going to be replacing everything. So in this formula, Q is known and delta T Lm is known. How? We did not find Q and delta T Lm in this question, but we did it in the last question. And it's going to be the same. The same procedure. You have the hot inlet, you have the hot outlet, you have the cold inlet, you have the cold outlet. Okay? So find out first of all, because you know the hot inlet, hot outlet, find out what is the Q. Then the same Q will be for the cold inlet and cold outlet. So find out cold outlet. Cold inlet is known. So now you know cold inlet, cold outlet, hot inlet, hot outlet. If you know all these 4 parameters, you can find log mean temperature difference. So these values you compute it, we compute it in the last numerical. Here they are just taken directly from there. But let's say you are solving this problem in the exam, you cannot say we did this in the last example. You have to do it there, like it is done in the previous example. Is clear? Anyways, so
Good question.
sorry.
Good question.
Yeah. So we have Q, we have delta T Lm. Okay. Let's talk about area. Let's talk about area. So what is the area of heat transfer? Okay, suppose I have this case. I have 1, 2, 3, 4, 5. Okay, so I have 6 spaces. So I have hot fluid here, cold here, hot here, cold here, hot here, cold here. Okay. So heat transfer will occur first of all from a surface of the plate. So its dimension is L by L, so L is square, multiply by the number of plates, right? So now let's see if I have how many gaps here? 1, 2, 3, 4, 5, 6. How many gaps? 1, 2, 3, 4, 5, 6. If I have 6 gaps, then how many plates will have the heat transfer? Okay, so hot to cold 1, then hot to cold second, then hot to cold third, hot to cold fourth, hot to cold fifth. If we have 6 gaps, then there are 5 full plates which are having the heat transfer. Why? Because the outer boundaries are insulated. There is no heat transfer from the outside world to the heat exchanger. So area will be what? Area will be L square multiplied by number of plates. Number of plates is number of gaps minus 1. Is it clear? So now we know A, okay. So if we know, so now we know all the terms in here. So we know A, we know delta T Lm, we know Q. Let's talk about U, okay. So if we substitute the values, it will become this thing, okay. Then now U is a function of L, and area is a function of L and N, okay. So now you just substitute all the values. In the end, you will get L is equals to 463 meter by N into N minus 1. This is mathematical manipulation. Okay. So you know delta T Lm, you know Q, you know U as a function of L, okay, because we determined this thing. This is HC as a function of N and L. We have HH as a function of N and L, right? We determined this thing. We have area as a function of L and N. So area as a function of L and N, U as a function of L and N, Q is known, delta T Lm is known. So we have one equation where L and N are unknown. So you can find L as a function of N. Is it clear? What's done here is mathematical manipulation. You can easily do this, understand this. There's nothing.
So I can design a heat exchanger through this equation?
Yes. For these conditions, my length will be a function of number of gaps that we have, like this. Now, if the gaps are 60, so first part of the problem is done now. First part of the problem was finding L as a function of N. First part of the problem is done now. Now we move towards the second part of the problem where we need to compare the pressure drops for this case to the last case. But in the last example, did we find the pressure drop? We did not find the pressure drop in the last example there as well. So we're going to do it again. Okay. So anyways, now we have the number of gaps 60. It is given in the problem. If the number of gaps are 60, find out the pressure drop. Okay. If the number of gaps are 60, then we know what is length, because length as a function of N we determined. So we know what is L, okay, and we know what is A, because A is L by N, okay, and we know what is hydraulic diameter, because hydraulic diameter is 2A, okay. So we can find out, okay, now for that, first of all, let's find out what is the Reynolds number. Because for finding the pressure drop, we need to know what is the Reynolds number. We did not find the Reynolds number for the previous cases.
We didn't calculate the pressure drop there.
Yeah, but now we have to find out the Reynolds number. Now Reynolds number is basically what? Reynolds number is rho Vd upon mu, right? Reynolds number is rho Vd upon mu. But velocity, okay, how to find velocity? For finding velocity, we have to use m dot is equals to rho Av,
Yes.
right? That's the equation that we have to use to find the velocity, because we know what is m dot, okay? Now here there is a catch. Look, this m dot depends upon what this area was. What this area is, what this is a cross section area through which the fluid is moving, okay. Now this m dot and A are interrelated. If you are using a cross section area only for one gap, then this m dot should be for one gap. But if you want to use the overall m dot, because in the question it is given overall m dot, overall m dot for the
So I
cooling
have to
fluid.
calculate overall cross-section.
So then you have to use the overall cross-section area if you want to use the overall mass flow rate. It's clear?
Multiply by 60, which is number of gaps.
Now, overall finding is very easy because this is L, this dimension is also L. So the overall cross-section area is L square. And half of it is being flown by hot, half of it is flown by cold. So L square by 2 is the cross-section area for the hot fluid. L square by 2 is the cross-section area for the cold fluid. Is it clear? Because we are ignoring the thickness of the plate. It's already said in the problem. Assuming thin metal plates, ignore the thickness. Is it clear? So now in this case your A will be what? L square by 2. Let's say you are doing for the hot fluid. Okay. So you write down, you know what is the mass flow rate of the hot fluid, which is the lubricating oil. You know what is the cross-section area through which it is flowing. You know what is the density. You can find out what is the velocity. Okay. Similar is the case for the cold fluid. So you see here, velocity is equals to m dot upon rho L square by 2. You understand how this L square by 2 comes?
Yes.
Because we are using the overall mass flow rate.
Yes.
So by doing that, the velocity comes out to be 0.0235 meter per second. Substituting it into this formula, we get the Reynolds number 141. Reynolds number 141 means it is laminar flow.
Yes.
Reynolds number 141 means it is laminar flow. For the oil-filled gap, that was for the water case, for the cooling water case. For the oil-filled gaps, again we have the mass flow rate. We'll find out what is the velocity. Substitute the velocity here. We get the Reynolds number 1.57. So here in this case, both are laminar flows, whether the hot fluid flow or the cooling water flow.
But you know that before.
We assumed
Before
that.
calculating how.
We assumed it before.
We just check the assumption.
Yes.
You said it is a fact. If it's the plate.
Yeah, it will. Actually, the thing is that it will be laminar flow, but previously we did not needed Reynolds number in any formulation. Now we need Reynolds number in the formulation. Okay.
At which temperature you give the viscosity?
Sorry.
The viscosity at which temperature?
Average. Average of inlet and outlet. We already know what is the average of inlet and outlet because by the time we were finding Q and delta T LM, we determined what is the inlet and outlet and we determined what is the average. Okay, so now the formula for finding the pressure drop. Formula for finding the pressure drop. That is chapter number 8, I think. Yes, also chapter number 8. Okay. So that's the formula, right? Delta P is equals to F rho V square upon 2D into length. Okay, that's the formula for the pressure drop.
Easy letter. We use it in project.
Nice, nice. You see, that's the advantage of doing projects.
Yes.
Okay, so that's the formula. Now, if it is laminar flow, then F will be, for laminar flow, F is 64 by Reynolds number. If it is not laminar flow,
You have to find
then you have to find it here. So go to the Reynolds number, then
It's very
go.
hard to find it all.
Hmm?
From this graph, it's very hard to find.
After detector a lot.
You have to find it.
You did have to go بالcalculation حقت ودي
Okay.
الأرقام.
There is a program for that without the chart
Without,
valid.
yeah, but these are all numerical programs. You have to solve the exam by paper, on paper.
Yes, in our projects.
Yeah, sure. There.
That's the answer.
In fact, we have EES software which has built in everything. So, anything. So now, because we know that it is laminar flow, so we are using F as 64 by Reynolds number here. Substitute all the values, you get delta P is equals to this thing. For the case of water, for the case of oil, delta P comes out to be this thing. Okay? So substituting all the values. But this is for the case of, no, this is for this example. Now we have to do the case for the example 1 as well. Again, the same formula. But for the example 1, we determined Reynolds number there before. Okay? The Reynolds number which we determined was, you see, that was the Reynolds number for inside flows. So this is turbulent.
Yes.
This is turbulent. Okay? And the Reynolds number, here it was 56 within the annulus flow. So that is not turbulent. This is laminar. So anyways, we find out again the pressure drops. Okay? Delta P and delta P for the two cases.
Rho for water.
Yes.
994 that density of water.
Rho for the water, you will take it between for the average temperature of T cold inlet to T cold outlet. Okay.
Cold inlet and cold out.
Average of the two. Yes.
What's the law for fraction?
What's the law for friction factor?
Yes.
Law for friction factor, if it is laminar flow, this.
No, it's for turbulent.
There is no law. You have to use the Moody chart.
What's that F equal 0.79 length?
Yes, this is for the smooth pipes. Okay, you can use this one for a smooth pipe if you want. But even if you use the chart, it's okay. A smooth pipe, you remember that one.
Wallah, the shot is very hard, Dr. Wallah.
No, you should know.
It's very small, you cannot see anything.
I will make a big one for you. Don't worry. I know you are uncomfortable reading the log chart, but you should know. Okay, so this last line is the smooth pipe. Okay, as an engineers, when you are studying the heat and mass transfer, when you are studying the fluid flow, fluid mechanics, Moody chart is something you should know. And since you are reluctant, I will make you use Moody chart. I'm telling you. You are reluctant. You don't want to use that chart. I will make you use that chart. Okay, you are exempted. So that's it. We have found out the pressure drops for all the cases as well. And this problem is done. Anything which you don't understand in the solution of the problem, other than being the fact that it's a very lengthy problem and it is involving so many things from the back as well. But if there is anything conceptually that you don't understand, you are free to ask. Good. So now let's move ahead. Now, so we did the heat exchanger analysis, and that was the kind of heat exchanger analysis was by using UA-LMTD, right? Q is equals to UA-LMTD. That was the main formula that we have been using. Okay, so this is one type of analysis. There is another type of analysis which is very common, and this, because LMTD method, this method which we have been using for the last two examples was known as LMTD method because it used delta TLM. This method has limitation, and the major limitation of this method is that you need to know the inlet and outlet temperatures for the hot and the cold fluid both. Because if you don't know, then you might need to do iteration. You might need to resolve it again. You first make an assumption, then you solve it, find out the outlet temperature, turns out that your assumption was not correct, and you have to iterate the problem. That's the big problem in this kind of problem solution. Okay, so by LMTD method, the limitation is that you might need iteration, but there is an alternate to this. Instead of using LMTD method, we can go towards another method, and that another method is effectiveness or NTU method. NTU is number of transfer units. At least you are aware of this terminology from chapter number 5, I think.
What?
In chapter number 5, there was NTU, number of transfer units.
No.
Oh, we studied five. No.
Okay, I'll show you later. There was exponent, inside exponent, you had the terminology tau, and it said that if that thing is known as NTU, if you put that as equals to 5, it will give you almost the same outlet temperature as.
Just effectiveness,
Okay, leave it. Anyways, so now let's move towards another topic, heat exchanger analysis, the effectiveness or NTU method. This is an alternate method. Okay. Now in this method, what we do is that in a sense, we find out the heat exchanger efficiency. Now, efficiency is what? Efficiency is what?
In terms of
What is efficiency?
outlet over inlet.
Outlet over inlet, right?
Sure.
Efficiency is outlet over inlet. But how are you going to define the efficiency of a heat exchanger? What is outlet? What is inlet? The main thing is the heat exchange which is going through. And the outlet of heat exchange, suppose you are saying that the hot fluid is providing heat, that's the outlet. It will be the same as the amount of heat collected by the cold fluid. So heat exchanger efficiency is not an appropriate term to define how well the heat exchanger is performing. Okay, so that's why we don't use heat exchanger efficiency. We don't define efficiency of heat exchanger. Rather than that, we use another thing to define how good a heat exchanger is performing, and that is the heat exchanger effectiveness. What is heat exchanger effectiveness? It's a ratio of how much heat transfer is going through divided by how much is the maximum possible heat transfer. So I have a heat exchanger and it is allowing a heat transfer of 10 kilowatts. Suppose its maximum possible heat transfer capacity is 20 kilowatts, so that means its effectiveness is 50%. It is running at 50% capacity. Maximum it can transfer 20 kilowatts. Right now it is transferring 10 kilowatts. Okay, so that's the heat exchanger effectiveness. How much heat transfer is going through divided by what is the maximum possible heat transfer. It's clear? Now how much is the heat transfer going through? The amount of heat transfer going through how much is the heat transfer going through its Q? Q is equals to m dot C delta T, which is T hot inlet minus T hot outlet, or Q is equals to m dot C delta T, which is T cold outlet minus T cold inlet. That is the amount of heat transfer which is actually taking place. Okay, what is the maximum possible? Okay, we know that m dot C, we can combine them together as to write capital C and capital C, right? And this is for the hot, this is for the cold, right? Now what's the maximum possible? Q max. Q max is equals to this is delta T. So it should be delta T max, right? But C minimum. Now the question arises, delta T max is understandable. If you want to find Q max, delta T should be max. But why C minimum? So let's explain this theory, this logic physically. Suppose instead of heat, you are transferring pen. Okay? So suppose you have, suppose Brady has 10 pens with him, and these has to go in my pocket, and my pocket has a size which can take 4 pen. Okay? So he has a capacity to give me 10 pen. I have a capacity to accept 4 pen. So how many pen will be transferred? 4. Although he has more, but I don't have capacity to take it. Suppose let's see the other way around. Suppose I have a pocket which can take 10 pen and Brady has 4 pen. So how much pen can be transferred? 4, because he has 4 only. Although I have more capacity, yet, so he has a capacity to give me, I have a capacity to accept. But the actual amount of flow will be limited by the minimum capacity. Get the idea?
Yes.
So that's the reason C minimum is here. Capacity of accepting heat, capacity of providing heat. The actual amount of heat transfer will be limited by the minimum capacity. So you understand this concept? So Q max is equals to C minimum into delta T max. Delta T max is what? We have 4 temperatures here. T hot in, T hot out, T cold out, T cold in. What will be the 2 temperatures that will have maximum temperature difference?
Hot, cold, cold.
So T hot inlet will be the highest temperature and T cold inlet will be the lowest temperature in the system. So maximum delta T max will be T hot inlet minus T cold inlet all the time. It's going to be like this. Is it clear? So that's Q max. If you know Q max, you can find out the effectiveness. Effectiveness is Q upon Q max. That's the effectiveness of heat exchanger. Effectiveness should be between 0 and 1. It can never go greater than 1. Greater than 1 means what? Q amount of heat transfer is more than the maximum possible? It's not possible. Okay? So Q must be less than Q max in any case. That's how we define the heat exchanger effectiveness. So Q is equals to, so if we know what is Q max, so multiply Q max, and if we know what is the effectiveness, multiply Q max with effectiveness, we'll get what is Q. That's it. Now this was about effectiveness. Now we have another terminology which is number of transfer units, NTU. Now number of transfer units has a formula this. It's UA upon C minimum. Whenever we write here C minimum, this means that when you have hot fluid and cold fluid, you don't know which one is the minimum. You will find out C for the hot, you will find out C for the cold, then make a decision which one is the minimum. And then use this. Sometimes the hot fluid one will be the C minimum, sometimes the cold fluid one will be the C minimum. Depends. Okay, so NTU is UA upon C minimum. Now NTU, number of transfer units, NTU and effectiveness, these two things are related with each other. These two things are related with each other. And what is the relation? The relation is given in the following tables. So effectiveness is a function of NTU and CR. CR is what? Heat capacity ratios. So heat capacity ratio, CR is equals to C minimum over C maximum. So CR is C minimum
Over C.
over C maximum. Obviously, you have two C's here. One is minimum, the other will be maximum. Okay. So based upon that, if it is concentric tube, parallel flow, counterflow, the relationship between effectiveness and NTU is this. Then counterflow, if CR is equals to 1, then this. If CR is less than 1, this. Shell and tube, one shell pass, multiple tube passes, this. N shell passes, this. Cross flow, both fluid unmixed, this. If one fluid mixed, one unmixed, depends which one side is mixed and which one side is unmixed. So C max mixed, C minimum unmixed, this formula. C minimum mixed, C max unmixed, this formula. For all heat exchangers, if CR is 0, CR 0 means what? CR 0. CR 0 means C maximum is infinity.
Can be infinity.
Yeah. C maximum will be infinity only in the case if there is condensation or evaporation occurring. When the condensation and evaporation is occurring, then the heat capacity is considered to have gone infinite. Okay.
Why?
It's too much compared to the regular flows, because now the latent heat is involved. It's not the sensible heat. Okay. So for the case of condensation, for the case of evaporation, this is the formula. Okay. Now, other way around, if we know what is the effectiveness and we want to know what is NTU, so then these are the set of formulas. Using those formulas, these graphs are made. You can use the formula, you can use the graph, whichever you find feasible. Okay. So if it is a parallel flow heat exchanger, then NTU and effectiveness, they are related with each other through this. And we have CR 0, 0.25, 0.5, 0.75, 1. Okay. Similarly, for the case of counterflow heat exchanger, this. For the case of shell and tube heat exchanger. For the case of cross flow heat exchangers with one fluid mixed, another unmixed, with both fluid unmixed. Okay. So these are the graphs. These graphs are derived from the formula. You can use the formula, you can use the graph, whichever you want to feel. You feel.
The dotted lines in there.
You see, oh, dotted lines? Yes. So dotted lines are, these are separate cases. These are separate cases. You see, this is for 1, this is for 1.33, this is for 0.75. Just separating. That's it. So anyways, now we move towards the problem solution using the NTU effectiveness method. Now we have two kind of problems. One is known as the design problem, and the other is known as performance calculation. You have to understand what does it mean. Whenever it is design problem, so you are at the stage of designing a heat exchanger. You don't know the dimensions, but you know what inlet and outlet temperatures you want. This is the condition, this is a design condition. When performance calculation is that, now you have a heat exchanger with you.
With the dimensions.
Okay, with the dimensions. You have the heat exchanger and the dimensions with you. Now, but you are supplying some amount of inlet temperature fluid, hot fluid and a cold fluid, okay? And now after heat transfer, you want to know that how effective your heat exchanger is working. So you are now you have the heat exchanger, and you just want to know that how good your heat exchanger is working. So that's the performance problem. So you have two different kind of problems: design problem, performance problem. In design problem, you don't have the dimension. You have all the inlet and outlets, and you want to know what should be the length, like the kind of problem we have been solving before.
The two.
Hmm?
The two problems.
The two problems. Okay? And the other kind is the performance type of problem. Now in case, let's say you go to a market, you purchase a heat exchanger. Now the heat exchanger is with you. You know the dimensions, you know everything about the heat exchanger. Now you supply the hot fluid, you supply the cold fluid, you want the heat transfer to take place, but now you want to know how good is your heat exchanger working. So you want to know the effectiveness. So that is kind of a problem, which is performance problem. So we're going to solve problem for we're going to solve problems related to related to design problem as well as performance problems. Let's first go towards the design problem. Hot exhaust gases which entered a finned tube cross-flow heat exchanger at 300 degrees centigrade and leave at 100 degrees centigrade are used to heat pressurized water at a flow rate of 1 kg per second from 35 to 125 degrees centigrade. This is a design problem. You know the hot inlet, you know the hot outlet. You know the cold inlet, you know the cold outlet. You know all the inlet and outlet temperatures. The overall heat transfer coefficient based on the gas side surface area is, the outside overall heat transfer coefficient is 100 watt per meter square Kelvin. Determine the required gas side surface area. So now you want to know the area. You don't know the dimension of the heat exchanger. You want to know the overall heat transfer area. That's a design problem. When you know all the inlet and outlet, but you don't know what should be the dimension of your heat exchanger. In this case, right now we are considering overall surface area of heat transfer. Okay, so we need to solve this using the NTU method. Now remember one thing, for parallel flow, you know how to draw the temperature distribution graph. For counter flow, you know. Cross flow, you will also draw it as a counter flow. Okay, so in parallel flow, both fluids are moving in the same direction. In counter flow, one is moving in this direction, other is moving in this direction. In cross flow, you will also draw it as a counter flow. Because in cross flow, we cannot go inside the page because they are crossing each other. Okay, we cannot do like this. We'll draw it as a counter flow. So we know what is hot inlet, we know what is hot outlet, we know what is cold inlet, we know what is cold outlet, we know what are the mass flow rates.
We know one mass flow rate.
Yes, we know one mass flow rate, we can find the other one. It's not an issue. Okay, so we need to solve the problem. So first of all, by using the NTU method, the most important thing is that we should know what is the C minimum, what is the C maximum. Okay. So we know the cold side water flow rate. So used to heat pressurized water at a flow rate of this. So for the cold side, Cc we can find easily because m dot C we know, Cp we know. Okay. So Cc we can find out. If we know Cc, we can find Ch as well by using these two equations. If you know Cc and you know Tc out, Tc in, you can find what is Q. This Q will be the same as this Q, and T hot in and T hot out you know. So you can find what is Ch. Is it clear? They did this all in one step here. Is it clear? So you find out, so C cold side was 4197, Cc hot side was 1889. So C minimum will be hot side. Okay, 189. Okay, now we can find out what is Q max, because Q max is equals to C minimum multiplied by delta T max, and delta T max is T hot inlet minus T cold inlet. We know what T hot, what is T hot inlet, we know what is T cold inlet. Substitute all the values, we know what is Q max. We know what is Q, we know what is Q max, we can find what is effectiveness. Okay, so we know what is Q. Q here they used it using the cold side. You can use the hot side, it's fine, because both Q's will be same. Okay, and substituting the values here in this equation, you get the effectiveness is 0.775. Now we need to know we need to find out what is the surface area, right?
Yes.
We need to find out what is the surface area. And for surface area, we need to know what is NTU. We need to know what is NTU. because NTU is something where surface area is there. NTU is equals to UA upon C minimum. So that's the area, right? That's the surface area. So for that, first of all, we need to know what is CR. CR is C minimum or C maximum. Substitute, this will be the CR. Now we can go into the figure 11.14 or use with the equation. Figure 11, if you go to figure 11.14, because what kind of, you have fin tube cross flow heat exchanger. Okay, you have fin tube cross flow heat exchanger, and you can see the figure here. Figure will also be there. You see here, there are lines here as well as there's the lines like this. So lines means unmixed. Whenever the lines are there, that means unmixed. So if the lines are only in one direction, that means this side unmixed, this side mixed. If the lines are like this as well as like this, so both side unmixed. So we have the both side unmixed case. So here this is the former, this is the graph for the both side unmixed case. Okay, we know what is the effectiveness. We know what is CR ratio. So from the effectiveness to the CR ratio, go find out what is NTU. Okay, if you are using the graph and there is a certain level of error there, it's okay, acceptable. Okay, but a certain level is acceptable. If the answer should be 2 and your answer is coming 5, well, cannot be acceptable. Okay. So anyways, after using that, it turns out that NTU is equals to approximately 2. Okay. So by using NTU 2, now you know what is C minimum. You know what is U side UH. You can find out what is the area. Okay. So this is a design kind of a problem where we do not know the area, but we know all the fluid inlet and outlets. That's the design. Based on the area, you can decide, okay, what will be the overall dimensions of everything. You know the overall surface area of heat transfer here. Is it clear? Is the solution clear? I know things are getting a bit more heavy as the time passes away, but you have to deal with it. Sorry to say.
Because you are the only fool.
Okay. Yes. Is given. Okay. Now heat exchanger performance calculation. It's a similar kind of problem, but this time area is given. So you purchase the heat exchanger already. So you know what is the area. But you want to know how this heat exchanger is going to perform. The effectiveness of the heat exchanger. I want to know that. So again, consider a heat exchanger design example of 11.1.3. 11.3, that's the same example, the last example that we did. Okay, that is fin tube cross flow heat exchanger with the gas side overall heat transfer coefficient and area of 100 watt per meter square Kelvin and 40 meters. So now this time the area is known, 40 meters square. The water flow rate and the inlet temperatures remain at 1 kg per second and 35 degrees centigrade. However, a change in the operating conditions for the hot gas generator causes the gases to now enter the heat exchanger with a flow rate of 1.5 kg per second and temperature of 250 degrees centigrade. Hot side temperatures are changed. Hot side temperature and the flow rate are changed compared to the previous problem. What is the rate of heat transfer by the exchanger and what are the gas and water outlet temperatures? So now you know the hot in, you know the cold in, you don't know the hot out, you don't know the cold out. But you know what is the heat transfer area for your heat exchanger. Okay, so it's like now a performance problem, performance calculation problem. Again, you will first draw this thing.
We draw. Yes.
Okay, and you will first have to find out CC and CH. Okay, you first find out CC and CH. After that, you will find out what is CR. Okay, then you can find out NTU because you know the area, you know U, you know C minimum, you know all these things. So you'll find out what is NTU. Now once you know NTU, then you can determine what is the effectiveness using the same graph. That graph was between effectiveness and NTU. Okay, now this time you don't know the effectiveness, you know the NTU. Last time it was the other way around. You knew the effectiveness and you wanted to find NTU.
He used the formulas here.
No, he again used the figure here.
Then Q max.
This is after finding effectiveness. This is after finding effectiveness. Okay. So first of all, we need to find out what is the effectiveness. By the graph again. Find out the effectiveness at around 0.82. Now once you know the effectiveness, then effectiveness is basically Q upon Q max. If you want to know, you know what is T hot in, you know what is T cold in, but you don't know what is T hot out or T cold out. You cannot find out T hot out and T cold out until and unless you know what is Q. For finding the Q, now you know effectiveness.
Q max.
So first you need to find Q max. Q max involves T hot inlet and T cold inlet, both of which you know, and C minimum. So you first find what is Q max. Once you know Q max and you know effectiveness, you'll find what is Q. Once you know Q, you substitute in these two equations to find T hot out, T cold out. As simple as that. Is it clear? So the two problems were just flipped. Yeah, reversed. In one problem, when it is the design problem, you don't know the area. When it is a performance calculation problem, you know the area, but you don't know the outlets for the hot and the cold side. Okay, that's it for today.